Hello and welcome back to differential equations. We are starting chapter 4 on Laplace transforms. So, what are Laplace transforms? This is going to be really cool, I promise you. And if you don't find this cool, you're on a wrong line of work. What we are going to do is we are going to take a differential equation eventually. I think in 4.3. We're going to take differential equation and transform it, using Laplace, into basic algebraic equation. When I say algebraic equation, I mean 2x plus 3 equals to 7, all right? And we're going to solve that for x. And then inverse Laplace is going to give us the actual solution of y that had all of the bells and whistles of a function. So, no, this is used. So Laplace transform is used to be the favorite technique for engineers. Today's favorite technique for engineers is called Mathematica. You just put the differential equation in, spits the answer out, and you're done. No one does these things by hand. But you have to understand that just 20 years ago, you did not have these computer tools, and 40 years ago, you didn't have calculator tools. So most of the stuff that you are touching and dealing with right now were developed without. So people actually had to do these differential, engineers had to do these differential equations using Laplace. Now, most of this stuff is lost now and pointless in courses, unfortunately, because you will never use any of this stuff. When you start working, you go to computer and you say, Igor, what is the, right? Presumably that your computer is called Igor. Mine is. So you are going to learn how to transform a function into what we call a Laplace domain, and then how to inverse Laplace, the Laplace domain, to get the regular domain back, and then we are going to solve differential equations using that. Solving differential equations this way, it's very powerful, very easy, but then inverse Laplace in some cases tends to be a pain because you will have to use partial fraction decomposition or something like that. Now, to understand where Laplace transforms come from, as we can start with the basic Taylor series, power series from Calc 2. You understand that a function f of x, right, was equal to some Cn x to the n, right? So that was in a good old Calc 2 days. Which means that what I'm going to do is I'm going to actually put f of x now on the right, and I'm going to say that the power series converged to a function. Now, what I have here is actually discrete function whose domain is 0, 1, 2, 3, 4, counting numbers, right? Positive counting numbers. And on the other side, I have a continuous function which contains 0.5 and 1.3 and pi and everything else, right? So we are going from the domain which was discrete to a function that was continuous. And that was Calc 2. Now, it wasn't posed and defined in these types of terms, so you might have missed that in your Calc 2 class. But there is this equivalency between the discrete world and the continuous world if you look at it this way. Now, clearly, we are adding infinitely many of these on the left-hand side, filling all the space. Right, air quotes right there. Now, the question is, can we make this discrete world here continuous world, right? So there is an input, and then we get a different continuous function on the other side. And the answer to that is obviously yes. What I can do is I can replace my Cn over there with a continuous function of some sort, and then have my variable. So let's say I use What happened? Nothing happened? Wow, history is really bleak. Oh, no, I'm not going to do any problems now. We're just deriving this thing. So, when you are looking at this, right, because the book didn't give you any of this stuff. They go, boom, here's your formula, go. Right? And you say, yay, partial fraction, by parts, and you solve all the problems. But where that formula comes from, right? It's actually the power series redefined for continuous functions. So over there, that Cn, which was a discrete function, I'm going to change that now into C of t. It's a continuous function. Now this t is a continuous t. And I'm multiplying that to the x to the t. And now, the way to see, it's easy to sum up there when you have your input to be 0, 1, 2, 3, 4. But now you can't use sum. What's the analog for continuous sum? Integral. Integral. Boom. Done deal. So what I did is I transformed the continuous, the discrete sum into a continuous integral. And now this is going to spit out something. We'll think of it later. But we just want to consider what's happening with the thing on the left. So now I have this function which is in terms of t, and we do not like integration of x to the t. So we can actually cheat by writing this x to the t as e to the ln of x, and all of that raised to the t. So this is a standard pre-calculus trick, right? Where you can replace anything you want that is exponential base right into e to the ln of that base, because now e and ln would cancel and you just get x to the t. So that's good. And now we don't like this ln x. So, and for purposes of convergence, you want it to be negative. So we define this ln x as negative s. That's just a change of variables. So now, limits of integration 0 to infinity. We're not going to forget the improper integral there, right? So now, what do I have when I put all of this together? I have 0 to infinity, c of t stays c of t, and instead of x to the t, I get to put e to the negative st dt. And now, you want to integrate this. When you integrate this, observe that the dt gets integrated out, because it's a definite integral. Improper, but indefinite. And all of the t's will die because you plug in 0 and infinity, and they all integrate out. What is the variable or parameter that survives?
S.
It's s. So we are going to get some other function, call it capital A, of s. Now, this is a mathematically completely new creature that you guys are now meeting. You have never seen a creature like this before. You have dealt with equations, you have dealt with differential equations, then you have dealt with operations like addition and stuff, and then you dealt with mathematical operators like derivatives and integrals. You haven't dealt with this type of a creature. This is called a transformation. Observe that on the left, you are feeding a function of t, and on the right, you are getting a different function in a different variable. It's a so your differentiation is going to feed into the machine, right, the differential operator. You feed a function f of x, like x squared, and it spits out a different function, 2x. But the input domain was x, and the output domain is still x. Which is the reason why, you know, I get every time, right, when you don't say, oh, ln absolute x. It has to be there. Absolute values must be there. Because your input domain on function 1 over x, which looks like this, is negative infinity to 0, union 0 to infinity. Your ln is only 0 to infinity. But with absolute values, you gain the other branch as well. So the answer now, domain matches perfectly the input domain. Because remember, these are numbers at the end. If I am to use 1 over x and x is negative 2, well, then I am integrating negative 1/2. And that gives me a number, which I have to match by the calculation on the other side. Right? Whether I'm going to integrate negative 1/2 dx, or I'm just going to plug in negative 2 here. If these absolute values were not there, you would not be able to do that. Right? So these absolute values here are not for decoration. Now, this is your world so far. Integration did the same thing. So integration, which is integral operator, you feed in function f of x into the integral operator, and it spits out a different function, again, in terms of x. Welcome to the world of transformations. On one end, you feed a function of x, and you apply the transformation, in our case Laplace, right, Laplace, and on the other end, you get a different function, a of s, let's say, right? So it swapped the domain completely. It's like jumped in a different reality. So when we are dealing with, in application, you might hear, right, when you start your 400 level courses in electrical engineering or whatever else, they will talk about the time domain and the frequency domain. And you go crazy. Ooh, what is that? Time domain is simply your integral in terms of t, which is the left-hand side. The frequency domain is its Laplace transform in terms of s. So maybe advanced physics, definitely a lot of engineering courses. When they start talking about time domain and frequency domain, that means the transformation from time domain to frequency domain happened, and that's Laplace transform was done. That's what it is. Now, it turns out that this Laplace transform is just like the gift from whatever to solve differential equations like this, which is amazing. And we'll see what amazing things happen as we apply this. So now that you know where the Laplace transform comes from, we can finally write the definition as it's in a book, which is technically what I have up there. It's just now they're using a different values. So Laplace transform, so this is a capital L in my world, of function f of t is given by the indefinite integral 0 to infinity e to the negative st times that f of t you want to transform dt, and that will spit out f of s. Lowercase f and capital case F are different functions. But we just want to associate the function coming in with the function coming out, because there's one-to-one correspondence there. So when we are defining Laplace transform, I'll put this on the cloud. This is your Laplace transform. Now, what does this entail? Do you see over here multiplication between these two? What kind of problem is this 100% of the time? By parts. Very good. It's going to be by parts. And by parts is going to deal with these things. When we have to do inverse Laplace, we are sometimes going to be forced to use partial fraction decomposition first, and then more integration by parts. Now, we actually don't do these integrals because we have Laplace transform tables. And in those Laplace transform tables, which will be provided for the exam, you guys will look at the problem, right? And then find on the table corresponding function f of s. You will write that one out. And I mean, you'll see how all of that stuff is done. You'll have plenty of stuff to learn without memorizing the table. Laplace transform is given to you on the cover of your textbook. And for the exam, I'm going to provide a copy of this, and I will remove one. I'm not telling you which one I'm removing, because that is going to be your question on the test. So, and in that case, you will be actually using partial fraction, you will be using by parts to solve that transform. So let's prove 2 from the chart, all right? So let's prove
no hints on what it could be?
I said 1 from the chart.
Yeah. So you do all that. No, I'm saying come test time. Which one it could possibly be?
So we want to transform f of t equals t into Laplace domain. Now you can open the chart, you use your eyes to look at it, and you know the answer is 1 over s squared, right? That's it. All the way on the bottom, left. You see t input, 1 over s squared output. Yeah. Ready? So to solve this problem, we are going to set up our Laplace transform. So Laplace transform of function t is the integral 0 to infinity e to the negative st times t dt. Now this is the cheapest possible, well, the second cheapest. The cheapest one is 1. So this is the second cheapest integral that you can see for Laplace transforms. And I hope you guys immediately see that this is improper integral of type 1, which means limit b goes to infinity of 0 to b. Right? So we get rid of that infinity by using the limit. And then we have t e to the negative st dt. Now we do this problem by parts. So if you remember your by parts, u equals t, dv equals e to the negative st dt, du equals dt, and v, which is the integral. Remember, you are integrating in respect to t, which means s is a constant. So the integral is the same thing divided by negative s. And then I use the arrow because it helps with the formula visually. If you do not know how to do by parts, well, there are lectures on how to do by parts. You should know because you did it. So this becomes t e to the negative st over negative s minus the integral of e to the negative st over negative s dt. So now we see that we can solve the second integral easily. The first one is already done. I forgot the limit. Okay. Limit b goes to infinity. Much better. There we go. Don't forget this limit. So now we have te minus st over negative s Negative and negative will give me positive here, right? We have 1 over s, and then when you integrate this, remember, I kicked this 1 over s out because it's a constant. We're integrating with respect to t. I kick 1 over s out, and then I integrate this one, I get e to the negative st, again a negative s in the denominator. All of this 0 to b. You all see that the word test is spelled out here?
Yeah.
All right, good. Just making sure that you can also.
There might, that might be your, it's an Easter egg.
That might be your clue. All right. So now, what I do is I just do the limit, right? So plug in b and then plug in 0 for all of them. So when you plug in b, we get b e to the negative sb divided by negative s minus 1 over s squared, and then we have e to the negative bt, no, negative sb. And now we need to plug in minus, we need to plug in 0 everywhere. Now when I plug in 0 for t, it kills this term, so that term is gone. When I plug in 0 on the next one, I have a minus, and then I have 1 over negative s squared. Because the 0 for t makes the exponent 0, e to the 0 is 1, so that's 1 over negative s, which is 1 over negative s squared, and then there is a negative also from the problem, right, from the fundamental theorem of calculus, right, for definite intervals. And now we also have the limit b goes to infinity. I hope I wrote that and disappeared. So now what happens? When I plug in infinity here, this term goes to 0, right? So this term goes to 0 because negative sb, that's negative infinity, e to the negative infinity, right? E to the negative infinity is 0, right, on this end. So, so Evan said that's infinity and that's 0. So, and we know that infinity times 0 could be infinity, could be 3/4, could be 0. Why is it 0? Growth rate of functions. This one is linear, goes to infinity linearly. This one is exponential, goes to 0 exponentially. Which one is stronger? Exponential, right? So there are these little tricks. Now you can always go and use the L'Hopital to actually work it out, right? Yep. And you will get that the answer is 0 on that one. This term again dies because this goes to 0. So that one goes to 0 as well. This is already 0, and then negative and negative. There's your s squared. So we learned that the Laplace transform of t is equal to 1 over s squared. Now you will, if you have the textbook with you, or you can just on your phone quickly Google Laplace transform table. The one that I solved right now, it's right here in the textbook where it shows the left is the function and the right is its Laplace transform. Now this table has 4 columns. It goes function, Laplace transform, function, Laplace transform. There are a lot of these. Now we are going to use about 6. That's a lie. We're going to use 10. But pushing 12, but that's it. Oh no, I'm going to work one more. I'm going to work out one more, and then you guys will practice 2 or 3 at home and have fun. Yes.
So we want to see what this is used for PreCalc for 2 seconds.
Are you disappointed?
A little bit. It's like, what is that?
What is this? Right now it's a peasant work. All right, because we are not. You are going to do this once on a test, and that's it for lifetime. all right, of doing the transformation by hand. And on your exams and the final, you will be using Laplace transform chart to solve the problem. And then when you start working, you'll just use Mathematica. At that point, the Laplace transform will be something that you just remember it existed, and then it sounds so familiar, but...
If somebody wants to know in the office, you can display your screen for them.
Perfect.
Yeah, you can go to a restaurant and do it on napkin.
Exactly.
Or show me your test that you got one from.
That's another thing. Oh yes, I had 100 on that. See you next week. So, should I transform e to the at? Should I transform sine t? Should I transform, well, sine to the at? Should I transform sine hyperbolic?
Well, let's do sine hyperbolic.
Kate, sine hyperbolic?
Yeah.
Everyone is happy with sine hyperbolic?
Hyperbolic KT.
That one wins?
Yes.
All right.
I know you love hyperbolic.
Yeah, I do. F of t equals sine hyperbolic kt. K is a constant. What are we at, 21 minutes? Let's sharpen the pencils and see if we can do it. $18 minutes. Fine, fine, fine. So we are looking for Laplace transform for sine hyperbolic kt. All right. We know the definition. It says integral 0 to infinity
Is that to do limit? No.
e to the negative st times sine hyperbolic kt dt. Now everyone is always excited about sine hyperbolic because that's one of the functions you don't see till Calc 2. But for me, that's the easy way out, cheap way out, because sine hyperbolic is what?
Cosine hyperbolic.
No I. This is sine hyperbolic. E to the kt minus e to the minus kt over 2. Exactly. So I get to do one of the very cheap problems. Now, what is the worst problem to do out of the ones that I suggested? It's sine, because you would have to do e times sine, and that's the integration by part twice, moving the integral on the other side, adding cost divided by 2, and then you, yeah. So that's the evil one. No.
That's the one I'm replacing.
Yeah.
So that's sine hyperbolic.
kt. So now we plug that in. I'm going to place the limit b goes to infinity, 0 to b, and I have e to the negative st times e to the kt minus e to the negative kt over 2 dt. Now the over 2 we can kick in front of the integral. So we have 1/2 limit b goes to infinity, and then I have 0 to b, and now 1/2 is out. This e to the minus st distributes, which means that the exponents add. You have negative st plus kt, so you can factor out t. What do you get? You get e to the k minus s t minus e to the minus k minus s t, all of that dt. 2 is in front. Minus k minus s. Yeah, I don't know why. Hold on, k. Oh my god. There we go. Are we green on this? All right. Now what I'm going to do is I'm going to, well, now we can integrate, right? But what I can do is I can actually pull minus signs from each one of these. So let me do that first, so it's not confusing later. Limit b goes to infinity, integral 0 to b, and I'm going to factor out the minus sign. So when I factor out minus, it becomes s minus k, minus e, and then minus s plus k dt. I forgot the t's. Yes, I forgot the t's, and that would spell do. I factor out minus signs in each one.
Oh, okay, I see what you did now.
All right, so now we get to integrate. Yay! So integral of e to blah is the same thing divided by whatever the constant is. So e to the negative s minus k t divided by negative s minus k minus, again, e to the minus s plus k t minus s plus k. Not dt, we are computing from 0 to b. Now, we plug in all the b's for t's, and then plug all the zeros for t's. So we have 1/2, limit b goes to infinity. No sneezing. So e to the negative s minus k b over negative s minus k minus, and minus give you plus, right? These two are plus. E to the negative s plus k b divided by s plus k now. That's it. And now we have minus. When I plug in 0 for the first one, it becomes t0, so the numerator becomes 1. So I have 1 over, and the minus in front changes this one to plus. And then I have a minus, and a minus, and a minus from the formula becomes a minus. And this is s plus k.
What was your third minus? From the formula you said?
Yeah, from the fundamental theorem when you do the right subtract f of a, right? So you have a minus over here, and minus from the formula, 3 minus on a pile to give you the minus there. Now, the reason why I factor out that minus, guys, is I'm going to plug this infinity for b, and there is a minus there. So minus infinity minus infinity. E to the minus infinity is 0. So all of these terms dead. Right? Right? Good? And perfect. We got it. Yay. So now what I have is 1/2. Limit is gone. And I have these two, which is 1 over s minus k minus 1 over s plus k. So find the common denominator and, deal with it. So we have 1/2 cross multiply. So s plus k minus s plus k, right? Divided by s squared minus k squared. So it's 1/2, yes, s dies, and you have 2k over s squared minus k squared. 2's cancel out, and you get k over s squared minus k squared. Bueno. Did you just say that after power series chapter? Did I hear it well?
I mean, it's all example activity, but,
Did you even try the Power Series homework?
I'm behind on homework, alright, I'll get there.
Yeah, you're in for it.
This is like the first time we're doing math homework in like a year. So all of this is so much in our math classes last.
Good to know. All right. Since you haven't done any math homework, now I give you the easy one to practice on your own since we have 10 minutes left. So transform f of t equals e to the at into frequency domain. He's Clive Warren, burn him. Yeah. Because the exponents lined up. We did not have e times sine or e times t, right? They all, so it was basic integration, technically just integrating e to the at. Well, if you, for these two types, yeah. So in the last two minutes, I'll solve this. What happened with the notebook?
I solved it.
You did?
Yeah, and I checked in the book. And it's okay.
No.
This is one you're going to use DV.
Yeah, you don't have to. This is a basic integral. It's a basic integral, this one, because you combine these, you add exponents.
And then you can multiply -3 times.
You add exponents. Yeah. So you just add exponents. Right? I don't. I can stay. What's the exam? Which exam?
Tomorrow's and the physics, Thursday's oral.
Oh yes, tomorrow is physics. I have one of the students in my calculus 2, God bless it, so who's going to take the physics test and then come and take the calculus test.
Why are the notes Yeah, we have physics Thursday and then we have statics Friday. And then we also have a quiz at work. Yeah.
We have a quiz at work. I forgot about that.
It's sentence. Okay, cards.
So we can learn words like AOE,
Unfit. Cards all like that.
Yeah, I'll have to know more about that. Just give me a second. All right, so we have now the limit. B goes to infinity when we integrate e to the a minus s t over a minus s from 0 to b. We have limit. B goes to infinity. We plug in b. So it's, oh, I forgot to factor out minus sign. So e minus s minus a, b over a minus s, and then minus, when you plug in 0, it becomes 1 over a minus s. So when you apply infinity, negative infinity, it goes to 0, and you are left with negative 1 over a minus s, but then you apply the minus sign, which switches signs, s minus a.
So always go to 0 first.
Depending on which way you put it together. So Laplace transform of e to the at is 1 over s minus a. Now, for practical purposes, which is differential equations later, Laplace transform of e to the 5t is 1 over s minus 5. Why did I pick 5? It's like the worst possible with s. 7t is s minus 7. There we go. No, you just solve for s. And then you inverse Laplace. So partial fraction decomposition will give you something like this, which actually gives you this back. So when you solve the algebraic equation, you get something like this. And you know that that came from here. So your solution will be y equals this. But that's 4.3. We have more formulas and more interesting things to work in 4.1, I believe. Linearity and existence. Oh, okay. Not that much. I will see you all on...
Are we going to be learning Euler's method? And
Runjakara, yes. That's numerics. So I will see you guys in 2 days.